Rutherford discovers the nucleus, right? He discovers that atoms are mostly empty, but that the mass is located in the center, in a tiny little dense region. He recognized that the nucleus had to have a positive charge. And so in trying to explain that, he did further experiments. We're not going to go into exactly what the experiments were, but ultimately he ends up proving that it isn't just a solid mass that is in the nucleus of the atom, but rather that the nucleus is made up of tiny little particles. And those tiny little particles, he says, must have a positive charge equal and opposite of the charge of these electrons that J.J. Thomson had discovered. And so in 1917, Rutherford sets out to, and does, prove that there are positively charged particles located in the nucleus of all atoms. He calls those protons. Unfortunately, what he hasn't accounted for with these little protons is all of the mass that is present. He has shown these particles are equal and opposite in charge to electrons and can therefore explain how atoms can be neutral, but he can't yet explain how the atom's nucleus can have as much mass as it does if it only has protons in it. So he proposes that there must be another particle there, but he isn't able to prove that there is another particle there. Later on, ultimately, there is someone who's able to prove it. Chadwick, Sir James Chadwick, discovers that there is this extra particle in the nucleus.
I have a very important...
This extra particle he calls the neutron because it is electrically neutral. What he proves in his own experiments that we're not going to go into is that these little particles make up the additional mass of the nucleus of the atom, and that they are roughly equal in size to a proton. Actually, they are slightly larger than a proton, but for our purposes, we'll just say they are equal. So they have no effect on the charge of an atom. They have only an effect on the mass of the atom. What hasn't been shown to this point is where these electrons are moving. What are they doing? And so it is later on that continuing work with the atom comes up with a theory about what the model of the atom should be, based not only on the fact that there are electrons and that there is a nucleus, but also where those electrons are actually found. With understanding of something known as the photoelectric effect, that you do not have to be responsible for, you'll learn more about that in chemistry, Niels Bohr began to understand that electrons must travel in somewhat of a path based on how much energy they have. So Niels Bohr develops a model of the atom in which he proposes that outside of the nucleus, the electrons can actually be found in set paths around the nucleus based on how much energy they have. And he called these paths around the nucleus for these electrons orbits, like the planets moving in their orbits around the sun. He suggested that the electrons with the least amount of energy would be in orbits closest to the nucleus, and that electrons with more energy would be in orbits farther away from the nucleus. He also proposed that if they are given the right amount of energy, these electrons can jump from one orbit to another. Bohr's model of the atom often becomes known as the planetary model of the atom because he describes the electrons' paths as orbits like the orbits of the planets around the sun. Although we're not going to get into all of the details, ultimately it is proven that Bohr doesn't have it quite right. Instead, it has been shown that electrons do not orbit in exact paths, but rather electrons are found outside of the nucleus in areas of high probability for locating an electron. The electrons cannot be located exactly, but instead we can describe where we might expect to find the electrons. So these regions, these areas where we would expect to find them, become known as orbitals, very similar to the orbits that Bohr was talking about. Because this is sort of a fuzzy area, no precise location, scientists begin calling this an electron cloud. This area of probability for finding electrons, but not being able to pinpoint their exact location. So how small are atoms really? Well, it's hard to imagine something as small as an atom. If you took something that is small in your life, like a penny, there are actually over 2 × 10⁻²2 atoms of copper in just one penny. I mean, it's hard to imagine a number that's that large. If we made those atoms as large as a grain of sand, which I think we can all agree is a pretty small thing, if we had as many grains of sand as there are atoms in this penny, we would actually be able to cover the entire state of California in sand. So atoms are incredibly small. It's so hard to wrap your mind around exactly how small an atom really is. So no one has ever actually seen an atom. We've only ever proposed what atoms are like. So as far back as Democritus, people have thought of atoms as these building blocks for everything. They imagine them in many different ways. Our current model is to imagine this tiny little nucleus with this fuzzy area called the electron cloud. But yet, we can't see atoms. Everything we touch, everything we feel, everything we see is made up of atoms, but we can't actually see them. The closest we come to quote unquote seeing them is to see a computer model of what the surface of a material might look like at the atomic level. And that's done using an incredibly expensive, extremely high-tech scanning, tunneling electron microscope. It is the closest we ever come to being able to see the surface of an atom. Again, not seeing it, however, because to see something, our human eye needs the reflection of light off of it, and single atoms are too small to reflect light.